Sup, God?
We have a new horn to propose to you.
Tell me more.
It has an infinite length, so it has an infinite surface area.
Oh, but it also has a finite volume, God.
Prove it to me.
Now, so, God, this is our graph of how we're going to create our horn. It's a 1 over x bound from 1 to infinity.
And as it gets closer to infinity, it's smaller and smaller and smaller until it's literally on the x-axis. So to create the horn, we rotated it around the x-axis.
Creating a shape that looks like a horn. And to prove that it has a finite volume, we'll take these lengths, which are these circles, and we'll call that dx. And to get the volume of the shape, we'll have to get the shape of the circle using the radius at a point, which is the length of 1 over x from the x-axis, and then multiply it by dx.
At a certain point. So we'll just be adding up a bunch of little circles with the radiuses being the height of the graph.
And we'll do that by using an integral from 1 to infinity.
Cool. So here is all our work for the horn. This is our main integral for adding up a graph with circles. You have pi times the radius squared times the length of the circle. For our radius, it's 1 over x.
And then down here, we evaluated our integral and we popped the pi out. And then we replaced the 1 over x squared with just 1 over x squared without the parentheses. And then we made it easier for us and made it equal to pi to the integral from 1 to infinity, x to the negative 2. And then that, after we did the integral, equaled pi times parentheses negative 1 over x from 1 to infinity. And once we had that, we had our whatever is an expression as negative pi over x from 1 to infinity. We were able to subtract by plugging in infinity, subtracted by plugging in 1, and we got negative pi over infinity, which is 0, minus negative pi, which adds pi. So that is our volume of the horn. So to find the surface area of this whole entire cone, we're going to do another integral, which means we're going to have a bunch of little pieces on the cone, or the horn, I should say. And each little piece unraveled around the horn is going to look somewhat like this. And this little part is what is the change, but this time instead of being a dx, because it's not a horizontal value, it's a, diagonal value, so we call it ds. And when we unwrap that, we get a shape that looks like this, kind of like this. And so we'll be using the shape and the sides of A, B to find our surface area. So similar to last time, our surface area will equal the integral, like Riley said. It's the integral from 1 to infinity, from 2 pi times r ds. And we already know that the radius is 1 over x accordingly to the graph. And then if we go down here, we also put the 2 pi outside. So 2 pi times 1 to infinity, integral 1 over x ds. And to find ds, we have to use Pythagorean theorem. And we do this by, if we look at the top of the graph right here, you know there's a slant, and that's very close to just a right triangle. And the change horizontally is dx, and the change vertically is dy. So then we use that theorem, and we get ds squared equals dx squared plus dy squared. Then we'll use a square root to get ds by itself, and then we get ds equals the square root of dx squared plus dy squared. And then
Pull out a dx.
Yep, finally we'll get ds equals the square root of 1 plus dy over dx squared times dx. And we do that by pulling out the dx from the square root.
And that allows us to do our final integral in terms with the dx for the change in length of everything. So basically what we did is we converted a little angular part of ds of the function, which is the little slight part around here, multiplied it by the area of a, which is just 2 pi r, and then we got able to have that for the final integral of 2 pi times.
To find dy over dx, we used the original equation 1 over x, integrated or derived that and got negative 1 over x squared.
And we were able to plug that into our final integral over here. So our final one is 2 pi times integral of 1 to infinity of 1 over x times the square root of 1 plus 1 over x to the fourth times dx. for our surface area. So in our surface area integral, you can see there's kind of this ugly part of the integral that's a square root. And every time inside the square root, it's 1 plus a fraction, and so we'll be plugging in these numbers for the fraction. And this square root is always going to be bigger than 1 because 1 plus something is always bigger than 1. And so then every time you go, as you go to infinity, when you plug stuff in there, it's just going to keep getting smaller and smaller, but it's still going to be bigger than 1. Therefore, this is always greater than 1, so we can make n.
Comparison. So the comparison that we're going to make is, we're just going to compare this integral and fraction to
So 1.
this. Because we know that this is always greater than 1, we know that 1 over x is less than that because it's going to multiply. So then we can just take the integral of 1 to x, and if we can prove that that goes to infinity, then we know that this goes to infinity because this is bigger.
Something bigger than infinity goes to infinity. Yeah.
So we'll compare it to this. So we have this surface area is greater than 2 pi times the integral from 1 to infinity, 1 over x dx. And doing that integral, we know that 1 over x, it turns into the natural log, so it's 2 pi times the natural log of x as infinity goes to 1, or 1 to infinity. And then obviously natural log of infinity is infinity, and therefore the surface area is infinity.
Bigger than
Infinity.
So it's infinity. Infinite surface area.